All right, good morning. Here we are again. So our goal today is to finish up chapter 13 and 14. Good luck to us all. We'll see how far we get. We'll stick with the schedule and the syllabus, and there's some built-in flexibility, so don't worry too much. You do have an exam next week, Thursday, already. So we'll get as far as we get, and we'll do our best. Stay tuned. I'll provide updates as to where you should be if you're on track. Right, so we had introduced 3 new classes of what I called organometallic reagents: organolithium reagents, Grignards, and cuprates. We're going to think about the organolithiums and Grignards as being mostly interchangeable, and then the cuprates as being special, sort of unique reactivity. On any of these, we're just scratching the surface, but one of the things that cuprates can do is react with acid chlorides distinctively from the organolithiums and the Grignards. So how organolithiums and Grignards react with acid chlorides is very similar to how lithium aluminum hydride reacts with acid chlorides. That is, you add the first equivalent, attack the carbonyl carbon, get a tetrahedral intermediate, the leaving group leaves, and that generates a ketone product, but you can't stop there because the ketone is also reactive towards the organolithium reagent. A second equivalent adds, and then you get to a tetrahedral intermediate that has no leaving group on it. There you're stuck. And then upon aqueous workup, you protonate the oxygen, negatively charged oxygen, to get this tertiary alcohol. Much in the same way that if you had reacted the acid chloride with lithium aluminum hydride, you would have got the primary alcohol with 2 equivalents of hydride adding. So sort of analogous reactivity that way. The point is you can't stop at the ketone, and therefore you can't really just have a strategy where you try to add 1 equivalent, that means 1 mole of organolithium reagent per mole of starting material, because as the initial amount of acid chloride starts to react and you start to form a little bit of ketone, that ketone now competes with the acid chloride for the remaining reagent, and you end up with a mixture of products. So when you're using an organolithium with acid chloride, you're just going to assume you have 2 equivalents, even if somebody doesn't write it there. All right? In contrast, the cuprates can stop at the ketone. They have different reactivity such that they can react with the acid chloride but not the ketone. This allows you to get a really interesting product from an acid chloride. You can get what I think your text describes as an asymmetric ketone. By that we mean the blue group that we added is different from the R group that's here. So in a synthesis question, if you need to make an asymmetric ketone, probably you're going to need to use a cuprate and an acid chloride. This is a strategy you can be using. Yes?
Is there a reason why usually in the textbook and practice problems they put 2 equivalents of a cuprate reagent instead of just 1?
I'm not, is there any reason? I don't actually think that they use 2 equivalents. Are you noticing that there's 2 things on the cuprate? Is that what you're talking about?
No, just sometimes they put a parentheses and then 2 and then liquid cuprate. Like
No, what you're actually seeing, I just saw it in the practice problem. Sometimes people won't write cuprates like this. They'll draw the cuprate reagent as follows. That means 2 ethyl groups attached to the copper and then a lithium counterion. That's fully equivalent to what I've drawn here. That's distinct from doing something like this, where in parentheses after a reagent you do this, and that says 2 moles of reagent for every mole of starting material. Yep, good clarification. Okay, others? Okay, that's the one interesting thing cuprates can do. Let's show you the second interesting thing cuprates can do. And we'll illustrate this sort of distinctive reactivity versus the organolithiums and the Grignards. what I'm drawing for you here is an example of what I will call an alpha beta unsaturated carbonyl compound. Unsaturated means there's a double bond. Alpha beta refers to where the double bond is. When we talk about carbonyls, this is the carbonyl carbon, this is the alpha carbon, and this is the beta carbon. We use Greek letters to describe distance from things, right? And alpha beta unsaturated carbonyl compounds have interesting reactivity. You can illustrate this, I guess, most simply by looking at the resonance structures that are possible. I can draw a resonance structure where I move the pi bond from the carbonyl carbon out onto the oxygen to give me a resonance structure where the carbonyl carbon is positively charged. But I could also draw a resonance structure where I move the double bond over to form a new pi bond between the carbonyl carbon and the alpha carbon, and that would leave a positive charge on the beta carbon. All of those are valid resonance structures, but they tell you that in the alpha beta unsaturated carbonyl carbon, there are two electrophilic sites. One is the carbonyl carbon and one is the beta carbon. Now, you can actually verify this with MO theory. I can draw real quickly for you an alpha beta unsaturated carbonyl compound in Spartan, and we can download it and look at the LUMO. And one of the things you see is the LUMO is no longer simply the pi star, but it extends over the whole molecule. Here's, I don't have a pointer in Spartan. So you see the red oxygen, the carbonyl carbon, the alpha carbon, and the beta carbon. And the LUMO actually spans all of those, which means that a nucleophile could attack the LUMO at the beta carbon or at the carbonyl carbon. You don't need to worry too much about what this LUMO looks like, but that's the MO theory explanation. In any case, what that means is a nucleophile that's going to react with an alpha beta unsaturated carbonyl compound, it's an example of a conjugated molecule, has to choose where to attack, at the alpha carbon or at the beta carbon. I'm sorry, at the carbonyl carbon or at the beta carbon. So that's where the difference between organolithiums and Grignards and cuprates come in. If we take this starting material and we react with an organolithium reagent or a Grignard reagent, I'm struggling to think what we should choose. All right, let's just do this one. Okay. We're going to see addition to the carbonyl carbon. That's going to leave the double bond between alpha and beta carbons intact. Okay, here is the group that we added in blue, the 4 carbons. I won't draw the mechanism for that because I think you can do it on your own. This would involve attack of the electrons from the bond between carbon and magnesium onto the carbonyl carbon, breaking the carbon-oxygen pi bond to get a tetrahedral intermediate with no good leaving groups. There you are stuck until aqueous workup, which protonates the oxygen, and that gives you this tertiary alcohol. Okay? In contrast, if instead we had used a cuprate reagent, the cuprate reagent is going to attack the beta carbon. And the way to show this, you could imagine this happening with any of the resonance structures shown above. The way to show this is you take the electrons from a bond between carbon and copper, and you attack the beta carbon. Then you push the remaining arrows like this. Doing that is not so very different from actually just attacking directly the resonance structure in which the positive charge was on the beta carbon. I've just copied that down from above. Either of those ways of pushing arrows for this reaction are equivalent to each other. What this does is it creates a new bond between carbon and between the carbon of your organo or of your cuprate reagent and the beta carbon of your alpha beta unsaturated carbonyl compound. So here's the new bond. There are the 4 carbons that we've added. I'm just going to label things to keep everything oriented. The new bond is with the beta carbon. And the molecule you have here is a resonance stabilized anion. We'll learn about such molecules later. They're called enolates, but you can see that the negative charge on the oxygen is stabilized by resonance with the pi bond between alpha carbon and carbonyl carbon. I'm not going to draw that resonance structure, but you should be able to draw it. It would have a double bond here and a negative charge on the alpha carbon. That's a resonance stabilized anion. There's no good leaving group attached. You're stuck at that point until aqueous workup. When aqueous workup happens, it's actually fastest to protonate on the negatively charged oxygen, and that gives you the following molecule. We will learn about molecules like this later in another chapter. This is called an enol, and it's in equilibrium with a ketone form. That looks like this. The process of converting from an enol form to a keto form is called tautomerization. I can't remember whether or not that came up in 351. Some of you may have seen that before, others you got nothing. If you had it with me, we probably skipped it, so sorry about that. Tautomerization is a type of isomerization where you're simply moving a proton around. Let me demonstrate. In the enol form, you have a bond between oxygen and hydrogen, and then you have a pi bond between carbonyl carbon and alpha carbon. In the keto form, you have a bond between carbon and hydrogen, and a pi bond between oxygen and carbon. Tautomerization involves moving only a proton and 1 or more pi bonds. It turns out that the keto form is more stable than the enol form, so that's what we observe. Going from the enol form to the keto form actually involves removing a proton from the oxygen to go back to the enolate, and then, so I'll draw that enolate intermediate one more time. And then adding the proton on the alpha carbon instead of on the oxygen, and that gets you to the ketone. I'm using equilibrium arrows, but understand that the keto form is going to be the major product because it's more stable. why am I bothering with this? Why didn't I just say, at this stage, you protonate on the alpha carbon and that gets you the desired product? Well, that would be conceptually easier, but it's not actually what happens. So I'm telling you what happens. It's also useful to know because you kind of have to know what the enol product is to understand how people will sometimes talk about the difference between these two reactions. The reaction of an alpha beta unsaturated carbonyl compound with an organolithium or a Grignard reagent versus with a cuprate. They will call this product, the alcohol, the product of 1,2 addition, whereas they will call the product of the cuprate reaction the product of 1,4 addition. All right? Now bear with me here. If we call the carbonyl carbon, if we call the carbonyl oxygen position 1, then in the product, it's easy to see that we added two things. The blue set of carbons and then the pink hydrogen to positions 1 and 2. That's the 1,2 addition product. In contrast, if you look at the enol product, it's clear that we added the blue thing to carbon 4 to position 4 and the pink hydrogen to position 1. So that's why that's a 1,4 addition product versus a 1,2 addition product. What I've just shown you here, the 1,4 addition product, is an example of a type of reaction that you will see again in this class. It is called, and this term is synonymous with 1,4 addition, it's called conjugate addition. It's addition of a nucleophile to the beta carbon of a conjugated system. All right, so that is the second thing that cuprates do differently. They attack alpha beta unsaturated carbonyl carbons at the beta carbon, and the product is this. If you compare that to your starting material, everything's the same except the double bond's gone. The beta carbon has the nucleophile from your cuprate, and the alpha carbon has a hydrogen. Yeah?
In the book, one way that it shows the reaction with the cuprate is that the electrons would go straight from the bond in the cuprate to the beta carbon, and then
Yes.
the electrons from that pi bond will just hop over to the other end,
Yes.
like to the next carbon, and put a negative charge on.
Yep, that is what you will see that option that you've described, which I'll just draw briefly here, is a resonance structure version of what I've drawn above. So what you just described is this: attack the beta carbon and electrons go on to the alpha carbon. That gives you this resonance structure, which hopefully, oops, I'm missing some carbons. Hopefully you can see that this is a resonance structure of this. Yep, that's totally fine.
Is
No
that
difference.
Like, if I understand it just like in that depth, is that enough? Or do you think it's more?
Let me see if I understand your question right. What I'm trying to tell you is what I've drawn here is exactly the same as what was drawn in the book. It's just a different resonance structure version of it.
Okay, sweet. Thank you.
Yep, go ahead.
Addition at the beta carbon, would that become a stereocenter out of the 4?
Yeah, good point. So we have the beta carbon, as you've noticed in our product, is a stereocenter. By drawing without dashes or wedges, I'm simply communicating you get both configurations. Yep. And actually, the alpha carbon is a stereocenter too. So we have the possibility for not just 2 stereoisomers, but 4 stereoisomers, 2 sets of enantiomers, which are diastereomers of each other. The text does not delve into that at all. There is likely some difference, and you can't favor one enantiomer over the other. You could potentially favor one diastereomer over the other. We're not worried about that. Okay, what else? Okay, so you need to be aware of that now. We have not had time, last time or this time, to talk about all the possible ways that you could react all of the starting materials we've dealt with the organolithiums, with the Grignards, and the cuprates. I have shown you the key examples. It's up to you to explore all the variations in the practice problems and make sure you can do it. You got enough tools to get the answers right, but I haven't walked you through every possible example. I'm trusting you to get that done, and if you can't, come talk to me. We'll work it out. One last thing we need to point out from this chapter, it's kind of included, well, there's actually two last things, so yeah. One is described in your text. I won't spend hardly any time on it here because it's review from 351. Your text points out that organolithiums and Grignard reagents can react with epoxides as well as nucleophiles. So here is an organolithium reagent, phenyl lithium. This is just a benzene ring where lithium is attached to one of the carbons. You can show this as a nucleophile. It's a strong nucleophile, so it's going to regioselectively attack the less substituted carbon of the epoxide. That shouldn't be a surprise to you. That's a principle from 351 to give you the product in which, with backside attack, doesn't really matter here because what we've made is not a stereocenter, but it's the product in which the group from the organolithium or the Grignard reagent here in blue ends up adjacent to the alcohol. Okay, so if you see a product where you have an OH and something that could have been a Grignard or organolithium reagent in sort of a 1-2 relationship on adjacent carbons, synthetically you can think I could have made that by opening up an epoxide. This is just another nucleophile you can use when you open an epoxide. All right, the last thing we need to say, and it's maybe one of the more complicating things from chapter 13, is that these reagents are, that we've talked about, the organolithiums, the Grignards, and the cuprates, we've already said we use them in aprotic solvent because they're strongly basic. And that creates problems for us because if we're using these reagents on molecules that have acidic protons, the acidic protons can get in the way of the reaction. Suppose a very simple reaction would be to take the methyl Grignard reagent, and suppose my desired product is I want to add the methyl from that Grignard reagent to the carbonyl carbon to give me the corresponding tertiary alcohol. The problem is, as set up here, that reaction doesn't work. And as you've read, the reason it doesn't work is that you've got an acidic proton, pKa around 16. You've learned to think of the Grignard reagent as basically being the methyl anion, which is a very, very strong base. So it should seem reasonable to you that instead of attacking the carbonyl carbon, it's easier and faster to remove the proton, which is much smaller than carbon and less sterically hindered, to give you this negatively charged oxygen. And you just spent a lot of money and time to make methane and negatively charged oxygen. And there you would stay until aqueous workup, and upon aqueous workup, You would simply protonate the oxygen, and you would be surprised to get that product. You'd be shocked, right? Well, sometimes, therefore, when we want to make this desired product, in order to get there, we need a workaround. And the strategy is called using a protecting group. We don't have a lot of time to talk about this, and frankly, there's whole textbooks on protecting groups. The concept of a protecting group is we're going to change the alcohol functional group into something else. That something else must lack the acidic proton. Putting that something else on must be easy, and it must also be easy at a later stage to remove that something else and restore the alcohol. Yeah?
I know we all be shocked to get that product, but is there any benefit to doing it that way? Like, is there ever a time where you're like, actually, no, I want to put it through this process because it means it'll be easier later on?
I mean, if your goal was to actually get something like this and use it as an intermediate, sure, that's fine. Our goal was to make this, though, and so, yeah. So again, the concept of a protecting group is we want to convert the alcohol into a functional group that lacks the acidic proton. Doing so must be high yielding, easy, efficient. 2, it must not interfere with any of the other functional groups in the molecule. And 3, restoring the alcohol must also be high yielding, efficient, and not interfering. Easy on, easy off. Okay? And there's a whole set of protecting groups or strategies you can use to do this kind of thing. And they all have different uses, different appropriateness for the situation at hand. Here, if we want to take this starting material, we need a reaction that only messes with the alcohol, leaves the ketone unscathed, and easy on, easy off. There's a lot of options. The one that's introduced in your text at this stage is called the silyl ether protecting group. It turns out that there are a ton of silyl ether protecting groups. It's sort of a cottage industry, and you use different ones for slightly different purposes. That's beyond the scope of the class. If you go work in a lab doing synthetic organic chemistry, you'll learn all about the different silyl ether protecting groups. I'm going to just introduce one here. This is the one that your text introduces, and it's one that's pretty broadly useful. So here is our starting material. Before this starting material ever sees the Grignard reagent, in a prior step, we do the protection reaction. And that is to use a reagent which is going to be unusual. This is going to be something you'll basically have to memorize because it involves silicon, and you haven't really learned how to deal with or think about the reactivity of silicon. So this has a silicon-chlorine bond, and then silicon is making 3 other bonds with carbon. Silicon is one row of the periodic table down from carbon. Like carbon, it can be bonded to 4 different things. That silicon should be sp3 hybridized tetrahedral. I'm just not drawing dashes or wedges because it's not a stereocenter. The reagents involved are this silyl chloride reagent. If you want to know what this is called, it's tert-butyl dimethyl silyl chloride. Organic chemists sort of fall in love with abbreviations, though not nearly so much as the biochemists do. So if you like acronyms and abbreviations, well, get ready for biochem because there's going to be a ton. Tert-butyl dimethyl silyl chloride, TBDMS chloride. And it turns out you also need a mild base. This is a base that's not going to interfere or react with the ketone. I'm drawing the structure for you. This base is called imidazole. Your text will sometimes, instead of drawing out all of that, will sometimes just write TBDMSCl, imidazole. I won't show you the mechanism of this reaction. Doing so is possible, but not really that useful to you, so it's sort of extraneous details. Essentially, you're doing an SN2 reaction at the silicon. You remove the proton from the alcohol, and you make a new bond between oxygen and silicon. The chloro is the leaving group. The methyl groups are here. And then you have the tert-butyl group there. This is called a silyl ether, because an ether would be if this was a methyl group and the oxygen were bonded to 2 carbons. It's a silyl ether because one of the 2 things attached to the oxygen is a silicon. Note that the silyl ether lacks an acidic proton, but the oxygen's still there. So that, and the reaction is very efficient, high yielding, easy to do, mild, it doesn't affect the ketone. People will abbreviate all of that as the following: TBDMS. Okay, so easy on. Then our strategy after we've done the protection is to do the actual chemistry we wanted to do in the first place. So the Grignard reagent attacks the carbonyl carbon to give me negatively charged intermediate, which on aqueous workup gets protonated to the alcohol. Notice that because the silyl ether protecting group lacks the acidic proton, that didn't interfere with the reaction. We've done the chemistry we came here to do. The hard part is now over. All we need to do at this point is remove the silyl ether protecting group. Deprotection. I won't show you the mechanism of this deprotection reaction. It's known, but it's not particularly useful or important for what we want to do. I'm actually gonna, though, instead of I wanted to copy. Let's just copy that. To illustrate it, I actually want to show you the structure of the silyl ether protecting group. Okay, your reagent for deprotection, and this is sort of alphabet soup today, is what I'm drawing for you here is a counter ion. The real business end of the deprotection reagent is the fluoride anion. This is tetrabutyl ammonium fluoride, or TBAF. TBDMS, TBAF, tuberculosis. I don't know what you're going to do to remember all of that. The fluoride anion is the business end of this reagent. The reason it works is because the silicon fluorine bond is very strong. So the fluoride ion is able to do a substitution reaction on the silicon that releases the oxygen. And you need water as well. Releases the oxygen, and then oxygen, the negatively charged oxygen, picks up a proton from water, and that gives you the desired product. Okay? So this is the protecting group. Protection, reaction, deprotection strategy is a common one for getting a molecule that you could not otherwise get because of the basicity of the Grignard reagent. Okay? That's protecting group chemistry, protecting group strategy. You'll need to do some practice problems on that to make sure that you've got the idea. Okay? Yes?
Are there any other like scenarios where you would need to use a protecting group versus like besides just the acidic protons?
Are there other situations besides acidic protons where you need to use a protecting group? Yes. And we will encounter some in chapter 14, which should have been like 5 minutes ago. So there we go. What else? Yeah.
The text mentions like a satellite anion.
Acetylide anion as
As like an organic,
okay. As a reactive organometallic reagent, yes. I'll just go back briefly. It turns out that you have seen, though you didn't realize it at the time, an organometallic reagent before. In 351, we dealt with it just like this, right? But, and we ignored the counter ion, but there was a counter ion. And you can actually make acetylide organolithium or Grignard reagents too. Yeah. So that's not necessarily something new. I think that's just connecting you to something that you've already done and been doing all along. Okay, yes?
If you use like an acetyl chloride to form the protecting group and form an ester, would that mess with the reactivity of the Grignard reagent?
Okay, that's an interesting question. So one of the things you could do, this is actually chemistry we haven't talked about, but could you have reacted this alcohol with this acetyl chloride to make an ester? That is a decent protecting group strategy. It turns out Grignard reagents react with esters too, though. So for this context, not going to work. Yeah. All right. Yes.
So sorry, just
That's
before
okay.
we move on, for the epoxides, do organocuprates also open epoxides?
Shoot, that's a good question. Do cuprates also open epoxides? I don't know the answer to that question. So let's see if I can find it in the book real quickly. The answer is, I got nothing. Sorry about that. So no, I won't expect you to have cuprates attack epoxides, even if you find out someday that it's totally possible. Fair? All right. Okay. Well, in chapter 14, we turn to focus on, chapter 13 was somewhat general in the sense that our starting materials were aldehydes, ketones, acid chlorides, esters, and some other carbonyl compounds. In chapter 14, we're going to focus in on aldehydes and ketones. Now, we're not going to repeat the stuff we just barely did with Grignard reagents, organolithiums, lithium aluminum hydride, sodium borohydride, and so on. We're going to focus on some other nucleophiles reacting with aldehydes and ketones. So let me give you an example. And this is going to be, in some ways, review, excuse me, of something that we discussed in chapter 13. Cn minus is a nucleophile. The counter ion is sometimes sodium, sometimes potassium. And then this reaction is also done in the presence of acid. I'm showing you the conditions that your book uses. I'm going to put a big sort of asterisk on this reaction by saying that don't ever go into the lab and try this one. There are better conditions for this. Cn minus reacts with HCl to make HCN, which is a poisonous gas. And I think if you smell almonds when dealing with it, you're already dead. So don't do this. There are actually better ways of doing this. Much less acidic acids you can do. But the point is that in this reaction, Cn minus as the nucleophile attacks the carbonyl carbon as you would expect to get a tetrahedral intermediate. Cn minus is a good enough nucleophile to attack directly. Once you get that tetrahedral intermediate, there's no good leaving group attached to the carbon, what used to be the carbonyl carbon. So we're stuck, but we have an acid present to protonate the carbonyl oxygen, and that gives you this product, which is called a cyanohydrin. There are some things you can do with cyanohydrins synthetically. We may learn about them a little bit later. Interestingly, if you're watching along, we just made a carbon-carbon bond, and carbon-carbon bond forming reactions are pretty useful in organic chemistry. But this illustrates is a classic illustration of a 1,2 type addition to a carbonyl compound, where the nucleophile gets attached to the carbonyl carbon and then the oxygen gets the hydrogen. So that's cyanohydrin formation. You're going to encounter that periodically in the chapter, and it's not hard, but that's sort of what we're doing. Okay, yes.
Why does the CN not just take the hydrogen from the HCl?
Right, this is something your text never answers. Why doesn't the CN just take the hydrogen from the HCl and then cause problems? You probably, yeah, I have no answer for that other than the actual conditions I've seen where people do this often involve much less acidic acids. You can kill two birds with one stone if you use the ammonium ion as the counter ion for cyanide. That comes with a proton that's not too acidic. And so that's probably the preferred set of conditions. I hesitated to show it to you because it's not in the text, but yeah. Okay. Let's talk about, while we're on the subject of amines, so that's cyanohydrin formation. Let's talk about using aldehydes and ketones to make imines and another class of molecules called enamines. That's how we write it. It is pronounced enamine. Don't say enamine. That sounds like it's your enemy, or rather that you're talking about enemas, which I suppose some of you are interested in medicine, so maybe that's interesting to you. But no, it's enamine and imine. All right. So let's start with an aldehyde. And let's react the aldehyde with an amine. And in most cases, and in this, well, for making an imine, our amino compound, this is going to be kind of confusing, right? We've got amines with an A, we've got imines with an I, and then we have enamines. So an amine is what I've drawn there. This is a primary amine. The nitrogen is attached to a primary carbon. And usually we need an acid catalyst. A common one that's used in your book is acetic acid. And various mechanisms can be drawn for this reaction. I will try to draw one that makes the most sense under the most circumstances. There are mechanistic variations. Your nucleophile is the amine. Your aldehyde or ketone is the electrophile. And then the acid is the catalyst. What is the acid there for? Remember that when nucleophiles attack carbonyl compounds, you get a negatively charged oxygen. And that's a high energy intermediate. And so if you have an acid catalyst, you can you can ease the formation of that high energy intermediate. What's thought to happen with when an amine reacts with an aldehyde is what I will show you here. Lone pair electrons on the nitrogen attack the carbonyl carbon. I believe your text shows the formation of a tetrahedral intermediate with a negatively charged oxygen, and then a new bond between nitrogen and carbon, and a positive charge on the nitrogen. There is evidence, however, and then at this stage your text would show the acid protonating the oxygen. That's fine. You can learn it that way. I don't have any problems with that. though I want to show you what the evidence says is often happening instead of that. Actually, let's just, I'm going to abbreviate our acid catalyst like this. Okay. What actually happens in a lot of circumstances is the combination of these first two steps in a single step. So I'll try to show you that now. What I'm showing you here, you'll learn later in biochemistry about something called general acid catalysis versus specific acid catalysis. What's thought to happen is that the nucleophile attacks the carbonyl carbon, the bond between carbon and oxygen breaks, pi bond between carbon and oxygen breaks, and electrons move out onto the oxygen. At the same time as negative charge is building up on the oxygen, the acid goes ahead and protonates the oxygen, and that takes you directly to the intermediate with the OH on it. What I've just showed you is called general acid catalysis. And it's actually a whole field of chemistry called kinetics to sort of study reaction mechanisms and determine, does the nucleophile attack first and then the proton gets added? Or does the proton get added first and then the nucleophile attacks? Or does it happen simultaneously? And what I'm telling you is, in spite of what's shown in the text, and there's nothing wrong with drawing the mechanism like this, what I've shown you here is probably what's actually happening. Yes?
What are the implications of the different mechanisms, especially what's
Dude, I just spent like 5 minutes telling you all of that. Of course it matters. What are the implications for this? If you want to understand how enzymes work, you need to understand why it might be bad for a neutral nitrogen to create a negatively charged oxygen. That should sort of just make you a little bit uncomfortable. And then to realize that if you had something present that could prevent that negatively charged oxygen from forming by adding a proton to it, either before or during, that might make the reaction faster. So that's the whole concept of catalysis, where you want to do something, but the transition state is so high in energy that you can't get there, but then you add a catalyst and now the transition state's much lower in energy. So yeah, what I'm trying to tell you is it's probably a lower energy pathway as the nucleophile attacks to add the proton. But yes, I suppose this is self-indulgent, because if I had just stuck with what was in the text, we could all move on with our lives. All right. All right. So we're not done yet. That's just the first step. We're kind of at a position where we're not totally certain what to do. It might have been reasonable at this step for a negatively charged oxygen to kick off the amine as a neutral leaving group. But now that we've got a neutral oxygen, it doesn't really seem that reasonable to kick off the amino group. What do we do at this stage? Well, it turns out that what we're going to do now is something that's going to happen a lot in chapter 14, and that is we're going to use the acid catalyst and its conjugate base to trade protons around and change who the good leaving group is. So what I will do from this point on, because these intermediates are identical, what I'm going to do from this point on applies to sort of both situations. It's likely at this stage that the conjugate base of our acid removes a proton from the positively charged nitrogen, generating this neutral intermediate. and restoring our acid catalyst. Your text points out that this intermediate is called a carbanolamine, except I can't spell carbanolamine. But the reaction isn't done because the proton can add to the oxygen or the oxygen can get protonated by the acid. And what that does is it turns the OH into something that is now a good leaving group. Green is for go. Okay? And now we can do something similar to what we saw in chapter 13. We have a good leaving group. Here's the alpha carbon, here's the beta position. We have lone pair electrons on the beta position and a good leaving group at the alpha position. These electrons can kick down, kick off the leaving group, and generate the following intermediate, in which I now have a nitrogen carbon pi bond, and water is the leaving group. Okay, questions about what happened there? Just using the acid to trade who's the good leaving group. And at this stage, we're going to regenerate our acid catalyst by taking the conjugate base of our acid and removing the proton from the nitrogen. To give us, restoring our acid and giving us this product, which is called an imine. Some biochemists will call this a Schiff base for reasons that are no longer important, but you'll still hear that term. Okay, so primary amines react with aldehydes and ketones with an acid catalyst to give you the imine product. Okay, questions about that? Now, I want to point out, this is something you're going to hate, so prepare yourself, that every step in this mechanism is totally reversible. And that makes the most sense when thinking about the various proton transfer steps in this reaction. If it's possible for this oxygen to remove a proton from the acid, then the backward step would merely be the conjugate base of our acid removing a proton from the oxygen to go backwards, right? It turns out each of those steps is similarly reversible. For example, here, removal of the proton from this ammonium ion or iminium ion to get the imine product and restore the acid. You could go backwards simply by having lone pair electrons on the nitrogen, remove a proton from the acid to go back to the iminium ion. And you could go from the iminium ion back to this intermediate by simply having water attack the carbonyl carbon of the iminium ion. When you do the reaction in the forward direction, just to summarize, this is called imine formation, but you can also take the imine and use an aqueous acid and that will hydrolyze the imine. So you've really just learned two reactions in one. You have imine formation, you got imine hydrolysis. Now when a reaction's in equilibrium like this, the question that often gets asked is, how do I get it to go the way I want it to go? And the answer is, you got to know what you're doing. And one of the things you can use if you know what you're doing is Le Chatelier's principle. Notice the thing that left during imine formation was water. So if you have a way to remove water from the system, you can push the reaction forward. And that is why when you're doing imine formation, probably you're in some kind of organic solvent that doesn't have a lot of water in it. And probably you're doing something along the way, some experimental technique to remove water. You'll learn this when you take the Organic 353 lab. There are various techniques you can use to remove water from an equilibrium. In contrast, if you want to hydrolyze an imine, then by all means use all the water you can in an acid, and that's going to help push the reaction forward. All right, I got to sneeze, and so that's a great time for a break. Let's take about 5 minutes, and we'll start back up at 9.